All right, there we go. How are you all today? Good, wonderful. Good weekend and good week so far? That's great. Well, I am having some technical difficulties today. Nothing is working. All right.
This is being done.
It's just like nothing. I have little arrows. I can't click on anything. And it did this earlier today too. Okay. Here we go. All right. For some reason, it just went on, so we're good. All right. Anybody have any questions before we get started? No? All right. So let me share my screen. No, I did not lose power. It's kind of interesting. It just things keep freezing up on me today. It looks like we're good. I thought maybe I was going to have to do the old log out, log back in thing, but seems like it's working okay. Okay, so let me know if you cannot see where it says earthquake right there with the little guy having a rough way to wake up in the morning or at
Literal
night.
S waves.
Yeah. All right. So natural hazard, earthquake. You guys remember the difference between a natural hazard and a natural disaster? We talked about this last week. What's the difference? It's kind of the difference when we talk about tornadoes. We'll learn about the difference between a watch and a warning. A tornado watch means it's a potential, it's a possibility. A warning means one has actually been seen. Hazard is potential. So natural hazard is the potential for something to happen that could harm people. And a disaster is the harm that happens as a result of the flood or earthquake or something, the landslide. So we're talking about volcanoes. Some of you guys might be there already. But before we leave earthquakes and start talking about volcanoes, I want to do a little bit of a review of earthquakes and then add a little bit of new information. So I have a couple I like this cartoon here. It was only a minor earthquake, but the Etch-a-Sketch gallery was ruined. I think that's cute. And what did one earthquake say to the other earthquake? It's not my fault. What did the ground say to the earthquake? You crack me up. You crack me up. All right. Just a reminder for you guys for the Kahoot lesson that is going to be coming up to make sure that you use your real name. Make sure that you use your real name on that because here we go here. There we go. I need to know who you are in order to give you credit. So the way I'm doing that is if you got 80%, you get 80% of the points. If you got a 70%, you get 70% of the points. So those of you who have done the review, I know a couple of you I haven't added in the points yet, but I'll be doing that tonight. What do you guys think of using Kahoot as a review? Give me a thumbs up if you like it. Thumbs down if you don't. What would you think of taking a test that way? Of instead of having a test, you had a Kahoot as an exam. You don't like it as an exam. Some of you do, some of you don't. Kind of, okay, review for sure. Maybe not for an exam. All right. One other thing I wanted to point out to you guys, I'm starting to see it happen a lot that many of you are only answering the first part of a multi-part question. So please be careful with that. If a question says name and describe something, make sure you name it and describe it. Don't just name it because you won't get the full points for it if you don't. So just be on the lookout for those. Okay. Have any of you guys ever experienced an earthquake? Valet, tell us what it was like.
So, there's been a couple, but one of the bigger ones I remember is me and my little sister, we were sleeping, and then, like, the door started rattling, and our dog jumped off the bed, and he just bit the door. It was really funny. That's
Yeah, animals don't quite know what to do when the ground starts shaking beneath them. Isaac.
I've been in one, but I can't remember. I actually didn't know.
Ah, so it happened, but you were told later?
Yeah,
Yeah,
we are due for another bad one around here.
yep, yep.
Hasn't happened in a while.
Yep, there you go. All right, somebody's in the chat. Let me see here. Yeah, Drake, you've had the same thing. Yeah, it's like you almost feel left out. Like you wake up in the morning and they say, "Oh, there was a little earthquake last night," and then you didn't see it. So yeah, earthquakes happen somewhere on Earth almost every day. The thing about most of them is most of them are so small we don't even notice them. They're just picked up by the equipment to test them. So do you guys have any guesses how many earthquakes are detected every year? How many do you think are in the whole globe? How many do you think are detected every year? Maisie,
I'm gonna guess 7.
more than 7. Drake, more than 500. More than thousands, Henry. Not millions. 500,000. There are actually about 500,000 small earthquakes detected every year. There are about 1,000 earthquakes somewhere on the globe every day. But of that 500,000, only about 100,000 are strong enough to even be felt by people. And only about 100 of them cause any kind of damage, even a little bit of damage. So major earthquakes don't happen very often. Usually a major earthquake will happen only about once every year. Now, you learned about the this Pacific plate. We talked about the tectonic plates. Well, look at the Pacific plate and then look at this red line around the Pacific plate. So most of the world's earthquakes, in fact, 9 out of every 10 of the world's earthquakes happen along that red line, along the edge of the Pacific plate. And we'll learn when we start talking about volcanoes, most volcanoes happen here too. Anybody know what this red ring here is called? Isaac.
So
Hey,
my
guys.
hand's still up.
Okay. Oh, okay. Okay. Yeah, Meredith and Jasmine have it. It is called the Ring of Fire. The Ring of Fire. So there's hundreds of active volcanoes around the edges of that Pacific plate in what we call the Ring of Fire. Now, most of the earthquakes happen there too. So because of that, they call it the Ring of Fire. Now, those people who live on the West Coast of the United States, that's right along the boundary. So here's our US right here. Look at the boundary of the Pacific plate right along where the West Coast is. That's why earthquakes and volcanoes both are more common along the coast, along the Pacific coast or the West Coast than they are anywhere else in the country. So scientists like to measure things, right? We're usually pretty good at finding ways to measure things, but think about how do we have any volcanoes in, well, that's a good question. I know there's some in the northern states above. I'm going to check that. Hold on just a second. There's, of course, Mount St. Helens in Washington. Are there volcanoes? Yes, California has several volcanoes, although many are dormant or inactive. You have Mount Shasta, Lassen Peak, Clear Lake Volcanic Field, Long Valley Caldera, Coso Volcanic Field, and Medicine Lake Volcano. Any of you guys ever heard of any of those? Yeah, so they're dormant. They're not ones that are likely to erupt, but we'll talk more about them maybe next time. All right. So like I said, scientists like to measure things. No, there are none that are active in California. You went to Mount Shasta. That's pretty cool, Aisha. No problem. All right, so how do you measure an earthquake? Well, we learned in this chapter that there's a couple different ways we can do that. Valerie.
I'm really sorry, but I just had a question. So, recently we went to Montana and we went to the geysers and shoot, how did I forget the name? Yellowstone National Park.
Right?
So, are those like what are those classified under? Are they like volcanoes or what are they?
So they're a place where there would be water coming up under pressure is what a geyser is, not lava. Lava is what makes it a volcano. So magma comes up and it becomes lava. So no, they are not volcanoes. They're like a different thing. They're just called a geyser. What? Let me check and see here if we can get a little bit more information. There has to be a heat source. There has to be a water supply. There has to be a crack somewhere underground in the rock that allows pressure to build up. And then when the pressure becomes too great, it erupts. It's superheated water that flashes out. Just really, you can think of a geyser as being like a volcano, only water instead of lava. Yeah, good question. All right, so there's a couple ways that we measure these volcano or these earthquakes. So one of them is what we call the Mercalli scale. So that's based on damage that's done. So people observe things, they have experiences, and they report those. And that's what they use in order to determine where something falls on the Mercalli scale. So take a look right there. Level 1, not felt except by very few under especially favorable circumstances. Now look at 4. During the day, felt indoors by many, outdoors by few. At night, some awaken, dishes, windows, doors disturbed. Walls make a cracking sound. Sensation like heavy trucks striking building. Standing motor cars rock noticeably. You can continue reading down that. Number 7 is everybody runs outdoors. Damage is negligible. That means not very much. In buildings of good design. Slight to moderate in well-built ordinary structures, considerable in poorly built or badly designed structures. Okay, just taking a look at that. Can you think of any problems with this scale? Henry.
Someone has to choose how much damage was done.
Right, right. Well, people have kind of different opinions about things, don't they? Different people have a different view. You might say, you know, this, so right here, felt by all many frightened and run indoors. Well, or outdoors, I think that's supposed to say. Some heavy furniture moved. Maybe you would say, oh, it was terrifying. You know, I ran outside, and I might say, yeah, it didn't bother me at all. So I might call it a 5, where one of you might call it a 7, or one of you might call it a 3. So when you depend on people to give a report of what something is like, you're going to get a lot of different perspectives. And this isn't based on equipment at all. This is just people. You're right, Valerie. It is not very scientific. So it also depends on where the earthquake happens. So an earthquake that's really far from a city could be huge, but not do much damage at all because there's nothing to destroy. Where one that takes place in a big city might be a kind of a mild earthquake, but it can cause a whole lot of damage. Kaylin.
One second, my Wi-Fi is being slow. So that is especially true in Alaska because of how many earthquakes we have. We have better like building structures to withstand earthquakes, so we don't really have building damage from big earthquakes. So
Right,
yeah.
right. Yep.
Oh,
There's
and I'm
ways-
burnt already. So
Isaac.
I think there's a place, if there's Japan, it's like a 7.2 earthquake that only killed one person.
That's pretty amazing, isn't it?
Mhm.
Yep, yep. All right, so another one that we use is that Richter scale. So this is the one that's the most well-known. This was developed by a guy whose last name was Richter, Charles Richter, back in 1935. And it's based on those seismographs. and it measures the magnitude of an earthquake. What do I mean by magnitude?
How big it is?
Yeah, how big it is, basically the size or the extent of something. So a Richter scale gives things a number between 1 and 9. So which is more destructive, a 1 or a 9?
9.
Yeah. Yeah, the bigger the number, the more destructive it is, the more powerful it is. So I said that it is based on a seismograph. I don't understand the comment. How many people? Oh, yeah, oh, injured. Okay, okay. Yeah, so this is a seismograph. That's what this machine looks like. So a seismograph is the instrument, and the printout that it makes is called a seismogram. So a seismograph is the equipment that measures the vibrations of the earth, and then it makes this graph, which is called a seismogram. All right, let's hold our conversations. When it goes like this, I'm going to miss questions. So hold on. All right, so taking a look right here, you can see what Richter scale means. So the value on the Richter scale goes up by tens. So a Richter scale 3 is going to be 10 times stronger than a 2. And a Richter scale 5 is going to be 100 times stronger than a 3. So every number up is 10 times bigger than the one that was before it. Okay, let's hold our conversation. Okay, guys, I don't want to have to shut off the chat, but I'm going to have to if we keep talking. I need you to be focusing here. Ballet.
You had us do a project where we had to measure the Richter scale, right?
Yeah, did that surprise
At
you?
first, yeah, I had to do the at first I was like, oh, is it really gonna take up all the space? And then I had to like restart it because I had to go outside because there wasn't enough space.
You had to go even bigger than you thought you were going to have to go. Yeah, yeah. Maisie.
What happens if an earthquake goes to like 10-9?
A lot of destruction. Yep, that's going to be a ton of destruction. So, yeah. All right. So if they are 10 times bigger than the one below them, if everyone is, an earthquake that measured a 6 would be 10 times as strong as one that measured a 5. But it would be 100,000 times stronger than one that measured a 1. It's a lot. So you add a 0 for every number up that you go. So an earthquake that measured a 6 on the Richter scale would be how much stronger than one that measured as a 3? Anybody want to do the math? Yep, there you go, Meredith. It's going to be 1,000 times as strong. Excellent, excellent. All right, now today we use a scale that's called the moment magnitude scale. It's a little bit like the Richter scale, but it's more accurate, and it gives scientists a better idea of the energy that's being released by the earthquake. Now, what's really kind of interesting is when you listen to the news, if there's an earthquake, they'll say Richter scale, but what they really mean is moment magnitude scale. Don't know why they do that, but they often do. So geologists use the moment magnitude scale, and it can be used for any kind of earthquakes. Some reporters may mention the Richter scale, but the moment magnitude is the one that they use. So who knows why? All right, let's talk about why we can't predict earthquakes. We've learned that it's really hard to accurately predict an earthquake. Why? Isaac.
Because it can change for one, and they're different. So, and it can occur in different places.
Right, right. Who else? Valet.
One, because yes, it's hard to predict where they're gonna happen. Also because the forces that cause the earthquakes are so deep below the surface of the crust that we can't even access that. So there really is no way to tell.
Right, right. Henry.
Because earthquakes happen when the tension becomes too high, and it's really hard to tell when the tension will become too great.
Right. So you can't tell just by walking over it. Ooh, this ground feels tense now. That doesn't happen. Kaylin.
Because earthquakes can really happen at any moment, at any size, any moment, and there's no way to tell when that's gonna happen. And like, it's not like a tornado or a tsunami, like there's signs before it happens, it just happens.
Right. There are some signs that they do monitor for, but they're not trustworthy because you can have signs and not have an earthquake, or you can have an earthquake when there were no signs indicating that one was coming. So it is very tricky. Maisie.
You cannot predict an earthquake because even if you have data, you need to you know like when it's gonna happen if you're like a good scientist.
Right, right, right. So we know that we've got these plate boundaries where one plate touches another plate, but they don't all behave the same way. And all the fault lines that we have, they don't behave the same way either. So remember, a fault line is a crack in the earth, but it's not just one crack, it's many little cracks all together. And because it's all so deep, we just can't get down there. We can't get down to take measurements way down where most of the activity is happening. The best that we can do is keep an eye on areas where we've had earthquakes before and where there may be ones again. So we know that they're more likely to happen on plate boundaries. And we know that they're more likely to happen in places where they've happened before. So we can use that knowledge to make some predictions about how likely it is that an earthquake is going to happen in a particular area. And knowing that can be helpful because then we can take precautions. Like Kaylin was saying, you can build things stronger if they're in areas where earthquakes are more common. They can design buildings in ways that they can withstand the stress of moving ground. Yeah, and they can find ways to keep people safe during an earthquake as well. Henry.
Why is the area in like Tennessee, and Arkansas why does that have a high risk?
So the ones that would be off of a plate boundary, you can understand, we can all understand why the ones that are plate boundaries, why they're more likely, because you've got two plates that there's a space kind of, like they touch one another. Why they're in the middle is a little trickier and usually has to do with a weakness in the lithosphere. Do you guys remember what the lithosphere is? That's the crust and the top part of the mantle work together. If you've got a weak spot there, there's an opening. Remember that magma underneath the surface, under the mantle, is always moving. We've always got this moving and it's under pressure. All it takes is a little crack and then you can either get some magma coming out in a volcano or you can cause the rocks to move. So that would be what would be happening there. So do you have a particular area you're wondering about, Henry?
Well, I was just wondering because there's like pink in the central US.
Okay,
So I just wondered.
let's see here. Let me see here.
Like on the
okay,
map.
These are called, yeah. So there are what's called intraplate faults. So these would be in the middle of a plate. They're a fault line that's in the middle. Remember too, let me see what have I got here. So if I've got these two plates right here, I know these are straight and a plate is real jagged. But if I've got these two plates here and this one moves this way, the whole entire plate's moving, not just the edge. So things here are moving too, things that would be in the middle. So when we've got a plate boundary here, right here, we've got a plate boundary, the Pacific plate runs right along here. When this plate moves, the whole plate moves. And that's going to cause everything, all the lithosphere is going to experience a little bit of motion. Now the plate boundaries, the plates don't move against one another very often, very quickly. Usually it's very slow little motions, but it's still going to cause a little bit of stress from that plate motion. Okay, there's another thing. Oh, this is interesting. Human activity. Yeah, so this is what's called induced seismicity. So people will do things that can lead to movement of the plates. So this says Oklahoma has seen a significant increase in earthquakes since the early 2000s and they've linked it to wastewater injection from oil and gas operations. So they actually will inject wastewater down into the ground, and that can cause pressure to build up there that could lead to an earthquake. That's interesting. That's a great question, Henry. Thank you. Kaylin.
I just wanted to say with the way we build buildings so that they can withstand earthquakes, it's kind of the same idea as with a bridge. We don't make them like, well, of course we make them strong, but we don't want them to like stay still. We like, if there's a big earthquake, you can actually see some of them like swaying
Yeah,
slightly.
they have to be flexible.
Yeah, that is a little scary.
Yeah.
Can I show you a cool rock that I found yesterday?
Sure.
Okay, let me get it. It's right here.
All right, Maisie, what's your question?
I was wondering why is the little like the little guy in pink?
So this one right here, you mean Hawaii?
Yeah.
So let me go back to this map where we're looking at the Ring of Fire. Right here. You can see right along here. So Hawaii would be kind of by the, in the center here of the Ring of Fire, but there would be, Hawaii is actually a series of volcanic islands. So there's a lot of seismic activity there where those islands are. So it would be located like kind of in here, in this area, right in there. Yeah, good question. All right, Kaylin, show us.
So
Not hearing you, Kaylin. Isaac.
You also have, you're muted, but the thing about Hawaii is if you think about it, it is the most dangerous, one of the most dangerous places, especially on the Big Island. Because one, you can get earthquakes there. That could cause earthquakes near it, causes tsunami. It should probably cover the entire island. And volcanoes can
Possibly.
blow in,
Yeah,
and
fortunately,
volcanoes
that
can blow you up.
doesn't
So-
happen very often.
Yeah, I'm just saying it's pretty
Yeah.
dangerous there.
Yeah, Kaylin.
okay, sorry, it's really loud in here, so I had to close the door, but it's still loud. So it's a volcanic rock,
Oh, that's very
and
cool.
it's like it has like white and reddish brown, and then
Yeah,
it's really cool.
that is cool. So you found that just outside?
Yeah.
That's
It
very
was
cool.
on the ground by our balcony
Awesome.
because
Very
we have a ground level thing.
All right. So one thing that we can do, we can't predict earthquakes and we certainly can't stop them, but we can try to protect the areas that might experience earthquakes. And there are some things that they do when they design buildings that help them to withstand force. Now, normally buildings don't have a lot of force on them, maybe a little bit of wind, but not a lot of force is usually put on most buildings. But in areas where there are earthquakes, architects will design earthquake resistant buildings, and they reduce the amount of force that the shaking of the ground puts on this structure. So a building that is symmetrical usually is better able to withstand the forces of an earthquake than one that's not. If a building is asymmetrical, like this one here, this would be asymmetrical. This one would be, it would be unstable because it's got a narrower part right in here. These are stable structures here. So ones that are symmetrical, ones that have these kind of shapes, all the parts of the building are going to experience the same force. No one part of the building is weaker than another. Right here, you can see this part here is going to be weaker than the part above or below. This one is going to be weaker on this side where it's not supported than this one is here. And of course, these with the little legs underneath them, those are going to experience all the force just on the legs. So L-shaped buildings, T-shaped buildings, some parts of them are going to be weaker. So they're going to experience more force during an earthquake. Another thing that is often done is that they will build these reinforcing beams. So buildings have columns in them. You can see the up and down columns in here, like right here, this is a column there. Those are usually made out of steel or a mixture of concrete and steel. And those columns are there to support the weight of the roof and then everything that's put into the building too. Now they're very good at supporting this weight when they're straight, but when they bend, they can collapse. They can lose a lot of strength and they can collapse. And an earthquake can cause a building to move sideways, and that can lead to the bending of the columns. So one thing that they'll do is they'll put these braces right here like that. These are called trusses, and they will put those in to strengthen the building. That will prevent the whole thing from going sideways and collapsing and falling down. You can even see those on bridges right here. These diagonal beams there, those are called trusses. So a truss is basically parallel beams with a smaller diagonal in between them. And that is much, much stronger than just diagonal beams alone. Another thing that they do is they work on the foundation of the building. So remember that soil is a combination of different ingredients. So what's soil made of? Anybody know what soil? There's 3 components to soil.
I was sediment, I would say, being there.
Not exactly sediment, but like, what is it made of? I don't know. Anybody know what the biggest bridge in the world is? Daisy just asked. I don't know the answer to that. Let me look. I bet it's in China.
The Kushan Grand Bridge.
Let's see here. Well, there's the
Yeah, it's in
longest one. The longest one is the Dangyang Kunshan Grand Bridge in China. The longest suspension bridge is in Turkey. The tallest bridge is in France. Yeah, what do we mean by big? The highest one above the ground is Piangjian Bridge in China. Interesting. Yeah, you're right, Henry. There's going to be sand, which, remember, sand is just crumbled rock. There's going to be soil, or sorry, humus. So humus is the remains of dead things. That's what gives soil its ability to grow things. And then clay. So clay, humus, and sand are the 3 things that soil's made of. Now, if soil has a lot of sand in it, especially if that sand is wet, it can behave like a liquid when it shakes. Think about that for a minute. When sand that is really wet shakes, it can behave like a liquid. So a building that's set on top of wet sand is going to either sink or lean over to one side. So when they have to build on sandy soil, like when they're making, on the shore, they're making a building on the shore, they'll drill these holes down into the sand, sometimes all the way down until they can anchor to a bedrock underneath. And then they will build the house or the building on top of those pillars that they've done there. So here's a picture that shows, what happens when the sand underneath, or in this case, it's clay, moves. So soft clay can be as bad as sand. It can actually, if it's real soft clay, it can also become almost liquidy and fall right away from the house. So hard clay and rock are the best foundation, the strongest foundation for a building. Another way that they earthquake proof buildings, is to separate the base of the building from the slab that sits on the ground. And they do that with a layer of what they call bearings. So usually the building is going to be attached to the slab in most houses. So right here's the slab. You can see this right here. Usually the bottom of the building will be attached to the slab. But when you're in an area where there is a lot of earthquake, they put something in between. These bearings could be made of rubber, they could be made of metal balls, they could be made of springs, and they absorb some of the motion and so they reduce the shaking that happens up above. Minerals are not organic, so they can't die. They also aren't alive, but it's dead animals and plants. Yeah, so the minerals would be part of the sand that is in soil. Yeah, very good. All right, now take a look at these. Anybody see anything wrong with these buildings? Would you want these in an earthquake prone area? No, you do not. So another thing that we have to consider is that the weight of a building matters. A building that's really top heavy like this, that's going to perform very badly when it's shaken. So these really should be upside down. The heaviest part of the building should be built down close to the ground. Something crazy happened a very big part of the city sank down. Now that whole area is a lot lower. Yeah, that's pretty interesting. Another thing that they have to consider is not to have loose objects on the outside of a building, like statues like this one can easily fall during an earthquake. So if someone's standing under that when the earthquake happens, that person could be in some danger there. Maisie.
What if there was no like earthquake in that direction? It just fell by itself.
Well, if there's no earthquake, nothing's going to happen. Nothing will fall. Yeah. All right. So often they'll use multiple factors in an area where there is an earthquake likely to happen. So they will use concrete walls that have those steel bars in them. They will use those shock absorbers at the base, and they will use these beams to cross brace it. So this is a really good earthquake prone building. And an important part of making buildings that can withstand the earthquakes is to test them to see if they work. So they use giant test shake tables like this one. So there's people in here. That gives you an idea of how big this is. There's people standing in there watching, and they put them on these platforms, and then they wobble them so that they behave just like they would in an earthquake. So the structures are built right there on that platform, and then they're tested to see how they stand up to these various shaking sources. Sometimes science centers will have shake tables that you can experiment with. Anybody ever been to a science museum that has a shake table on it that you can stack up blocks and then make it shake and see how well you did? Yeah, they're kind of fun. They are kind of fun. All right, and of course, earthquakes do a lot more damage than just buildings. Here you can see a road that has been, completely destroyed by this earthquake. Here's a couple of interesting earthquake facts for you. So the largest earthquake recorded in the United States was in Alaska. No big surprise, Kaylin, right? It was a 9.2 that struck Prince William Sound back in 1964. Big earthquake with that one. And the largest recorded earthquake in the world was a 9.5 in Chile in 1960. Kaylin.
So wait. Hang on, I'm forgetting what I was saying.
Okay, that's okay. We'll come back to you. The earliest recorded earthquake in the United States was felt back in 1769 by this guy. His name is Gaspar de Portola, and his group was camping near Los Angeles, and they felt that that earthquake, and they recorded that. Kaylin.
So I went to a summer camp when I was going into 6th grade, and we did a fun thing where we would have a team of 4 people, and we would build a bridge that had to withstand an earthquake. And we were using these like little plastic things that like stuck together. And when we were done, we put them on a shake table. Like we would use these wooden blocks and stick them through the bottom and like stick them down. And then so my bridge actually won. Yeah.
Great. Congratulations. Well done. All right. So this is a picture here taken from the sky of a big fault in California. This is called the San Andreas Fault. And you can see there, it's not just one fault. It's actually a zone that's made up of many segments and many cracks, and movement can happen anywhere along any of those cracks. So the San Andreas Fault is more than 800 miles long, and in some places it goes as much as 10 miles deep. So you got a crack in the earth, 800 miles long and as many as 10 miles deep. Now, the origin of the name San Andreas, they're not completely sure what got that name, but they think that that a man named A.C. Lawson named the fault from the valley. There's a San Andreas Valley that he named it with. So do you guys know which state in the US has the most earthquakes? What do you think, Isaac?
Touching the US or any?
Any US state.
Probably Hawaii, or I don't know. I would say something like Hawaii, California, or Alaska.
What do you think, Drake?
I'm not sure though.
Oh, sorry. I thought you were raising your hand. I just saw your hand there. Henry.
Alaska.
Yeah, you're right. It is Alaska. So look at the dots right there. Alaska's one is definitely the most earthquake prone of our states. And it's also one of the most active regions in the whole world. So Alaska experiences a 7 or greater almost every year. And it gets an 8 or greater about every 14 years. Yeah, yeah. One interesting thing too is that moonquakes happen. There are earthquakes on the moon. They don't happen as often, and they're usually smaller in magnitude than the earthquakes on the earth. And it appears as though they're related to the stress that's caused by the earth and the moon with their gravity pulling on each other. And they also tend to occur deeper. They occur usually about halfway between the surface of the moon and the center of the moon. Yeah. Sunquake. So there's no solid on the sun. So, you know, there aren't like plates and things to move in the sun. So we have different things happen with the sun. We've got solar flares that happen, large eruptions of energy that happen, but not exactly sunquakes. So look at this. This is called a seiche. A seiche is what happens in swimming pools and enclosed bodies of water like a lake that would happen during and after an earthquake. Basically, it's an internal wave. In other words, it's the sloshing of the water out of your swimming pool or out of a lake caused by the ground shaking. And this can go on for just a couple minutes, or it could go on for hours, long after the force that generated it is gone. So that's be pretty fun to be swimming in that. Here you can see a swimming pool at the University of Arizona. They lost water by one of those seiches sloshing around, and those guys are getting slammed around pretty good by that seiche. All right, so let's take a look here at the earthquakes that have happened in the last week in the United States. So right here, this is in the past week. So right here's Alaska. This map, you're going to look from here, from this line here to this one over here. So this is North America, South America, and here we have Asia and Europe and Africa and Australia right there. Okay, so take a look at the ones that have happened in the last week, and you can see, we can even zoom in and get a little bit bigger picture here of just the US. So we can definitely see our ring of fire, can't we? Lots happening around this Pacific plate. There have been a couple in the inner part of the United States as well. So zooming in yet again, you know, we can see this right along here. Yeah, pretty interesting. Maisie.
Can someone get easily hurt in an earthquake or a tsunami?
Yeah, you can get hurt. Many people die when it's a big earthquake. Yeah, part of the reason is because the earthquake causes damage to buildings. And if a building falls, it's going to kill whatever people are in there. Yeah, that's very good. Very good point. All right. Anybody have any questions about earthquakes? All right, I got a Kahoot for you. An earthquake Kahoot. You ready? All right, here we go. www.kahoot.it, and our game pin is 689722. 689722. All right, everybody's coming in, good. All right, are we ready? Anybody need more time? All right, I'll give you
I
one
need a
more
second.
minute.
I need a sec. Yeah, I need trying to get it work.
Miss Joseph, mine won't let me in, so can you put it on the chat?
Yeah.
Please. Thank you.
You're welcome. There you go. 689-722. You guys, if you have a QR scanner on your phone, that's an easy way to get in. You just open up your QR code scanner, scan that up at the top there, and it'll get you in real fast. All right. 5, 4, 3, 2, 1. All right, here we go. See how well you know your earthquakes. The definition of an earthquake is a sudden motion along a fault. Excellent. Very good. All right. V got there first. Question 2. A seismic wave is a wave of energy traveling through Earth away from earthquakes. All right. So I like the a lot of people waving at the same time. And this one's funny. Clearly seismic activity. All right. Question 3. Divergent plate boundaries divergent divide. They pull away from each other. Well done. Remembering that little song, divergent divide, convergent collide, transform tectonic plates slide. All right, here we go. Aisha's in first place. Question 4. Convergent plate boundaries. Convergent collide. They push toward each other. And a quake that measures a 5 on the Richter scale is how much stronger than one that measures a 3? That's going to be 100. 100. So a 4 would be 10 times greater than a 3. And then a 5, you add another 0, 100 times. And then a 6, you add another 0. That'd be 1,000. And then a 7, you add yet another 0. You just keep adding zeros each time you go up one on that Richter scale.
You said 1,000 earlier today in class.
Not then a 3. I think it was a different number.
No, it was a 3.
All right. Well, that it is 100. All right, here we go. Question 6. A machine that measures vibrations of the earth is a, what do we call the machine? Oh no, there's 2 that are identical. All right, well, I'm sorry about that one. I wish there was a way I could delete one after. There is not. So, all right.
So both should have been.
One of those is supposed to say Graham. Sorry about that. All right. Question 7. Most earthquakes occur along tectonic plate boundaries. True or false? That is going to be true. Most of them happen right along those boundaries. In fact, most of them happen along the Ring of Fire with around the Pacific Plate. At transform plate boundaries, 2 plates move past each other horizontally. Yeah, they're not going to move up and down this way. They're going to move this way, even with the horizon. All right. Question 9. The point on Earth's surface right above where an earthquake starts is called the epicenter. It is called the epicenter. Question 10. The center of where an earthquake begins is called what? The part down under the Earth. Focus. The focus is down under. Right above it is called the epicenter. All right. Question 11. The measure of an earthquake's strength is called what? How strong is it? It is called magnitude. Excellent. Question 12. Structures made of brick and concrete are? They are not very flexible. Remember, brick and concrete kind of stay still. So they're pretty easily damaged by earthquakes. As Kaylin was telling us, they make things to be able to flex just a little bit, to be flexible, so that when the shaking happens, they can bend a little bit with it. So brick and concrete are not the best building materials to use by themselves in an area that is prone to earthquakes. Question 13. The scale most often used to measure the magnitude of an earthquake is? It is the moment magnitude. Remember, Mercalli's the one that's based on people's opinion. The Richter scale is a little older. We still use, a lot of reporters still use that name, but what scientists use now is that moment magnitude scale.
I feel like everyone should got that one because it says actually magnitude in it.
Yeah, you're right. You're right. Kind of a hint. Structures made of what are more flexible and likely to survive strong ground shaking? Wood and steel. Yeah, not brick and concrete. Yep. All right, couple more questions. Earthquakes and tsunamis can affect human societies. True or false? That is true. You want to see the little cartoon? It's only an earthquake. Now go get my cat carrier and go, kid. Yep. All right. Jasmine's in the lead. Question 16. Homes, buildings, and bridges cannot be strengthened to decrease earthquake damage. True or false? That's false. We learned all about ways that we can strengthen them. Yeah, lots of ways. All right, here we go. Last question. What are giant ocean waves, which may be caused by earthquakes on the seafloor? Yeah, they are called tsunamis. Tsunamis. All right, excellent job, everybody. Let's see how we did here. In third place, the bomb. In second place, Henry. And in first place, dun, 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 Jasmine. All right, well done. Great job, great job. All right, anybody have any questions about earthquakes before we say goodbye? Start learning about volcanoes. All right, if not, I hope you have a wonderful week and I will see you next time.
Thank you.
Have a great day, everybody. Thank you. You're
Bye.
welcome.
Thank you.
Bye.